Welcome to Module 6 Machine Learning Fundamentals. Machine learning is a crucial area of data science that focuses on building models that can learn from data and make predictions or decisions. It's the core of many systems, including recommendation engines, predictive maintenance, and natural language processing applications. In this module, we will dive deeper into machine learning concepts, algorithms, evaluation methods, and real-world applications to provide a comprehensive understanding of the subject. Key concepts in machine learning. 1. Types of machine learning. Machine learning algorithms can be classified into three primary types based on the nature of the data and a problem being solved. Supervised learning. In supervised learning, the algorithm is trained on labeled data, meaning each input data point is associated with a corresponding output, label. The goal is to learn the mapping from inputs to outputs. Examples. Regression tasks, predicting continuous outcomes, such as predicting housing prices based on features like square footage, number of rooms, and location. Classification tasks, assigning data to predefined categories, such as identifying spam emails or classifying images of animals into categories like cat or dog. Unsupervised learning. Unsupervised learning involves training on data without labeled outputs. The model is tasked with discovering patterns, structures, or relationships within the data. Examples. Clustering, grouping similar data points together, e.g., customer segmentation for marketing. Dimensionality reduction, reducing the number of variables under consideration, often used to simplify models or to make data easier to visualize. Reinforcement learning. Reinforcement learning focuses on training an agent to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties based on its actions, and its goal is to maximize long-term rewards. Example. Game playing. A reinforcement learning model can be used to train an agent to play a game like chess or Go by exploring different moves and adjusting its strategy to win. 2. Common machine learning algorithms. Several machine learning algorithms are widely used across different types of tasks, and each comes with its own strengths and weaknesses. Linear regression. A simple algorithm used for predicting continuous values. It assumes a linear relationship between the input features, independent variables, and the output, dependent variable. Example. Predicting the price of a house based on its square footage and number of bedrooms. Logistic regression. Despite its name, logistic regression is a classification algorithm used when the target variable is categorical, especially in binary classification tasks. It calculates the probability that a given input belongs to a specific class. Example. Predicting whether an email is spam or not, binary, spam equals 1, not spam equals 0. Decision trees. A decision tree model breaks down data into smaller subsets by making binary decisions, splitting based on feature values. It creates a tree-like structure where each node represents a feature, and branches represent the decision made based on that feature. Example. Deciding whether a customer will buy a product based on features like age, income, and browsing history. K-means clustering. K-means is a type of unsupervised learning used for clustering. It divides data points into K-clusters based on similarity, minimizing the variance within each cluster. Example. Segmenting customers based on purchasing behavior for targeted marketing campaigns. Random forest. A random forest is an ensemble learning method that combines the predictions of multiple decision trees to improve accuracy. It reduces the risk of overfitting compared to individual decision trees. Example. Predicting customer churn based on various features like contract duration, usage, and demographics. 3. Model training and evaluation. Training a model. The training process involves feeding data into a machine learning model and adjusting the model's parameters to minimize error. In supervised learning, the model learns by comparing its predictions to the known labels and adjusting its internal weights accordingly. Training data versus test data. A dataset is typically divided into two sets: training data, used to train the model, and test data, used to evaluate the model's performance. The test data should be kept separate from the training data to avoid overfitting. Overfitting. Overfitting occurs when a model learns the training data too well, including noise or irrelevant patterns, which reduces its ability to generalize to unseen data. To prevent overfitting, techniques such as regularization, cross-validation, and pruning for decision trees are used. Underfitting. Underfitting happens when a model is too simplistic and cannot capture the underlying patterns in the data. This often occurs when the model is too constrained, e.g., a decision tree with too few levels, or if there is too little data. For model evaluation metrics. The evaluation of machine learning models is crucial to determine how well they perform and whether they can be used in production. Accuracy. Accuracy measures the proportion of correct predictions made by the model. While it's a useful metric, it can be misleading when the dataset is imbalanced, e.g., 95% of the data points belong to one class. Precision and recall. Precision is the proportion of true positive predictions among all positive predictions made by the model. Recall, also known as sensitivity, is the proportion of actual positive instances that were correctly predicted. Precision equals TP/TP plus FP. Recall equals TP/TP plus FN. F1 score. The F1 score is the harmonic mean of precision and recall, providing a balance between the two metrics. It is especially useful when dealing with imbalanced datasets. Confusion matrix. A confusion matrix is a table that shows the true positives, TP, false positives, FP, true negatives, TN, and false negatives, FN, for binary classification problems. It is a powerful tool for visualizing classification performance and calculating other evaluation metrics like precision, recall, and accuracy. 5. Cross-validation. Cross-validation is a technique used to assess the performance of a model by dividing the dataset into multiple folds. This helps to ensure the model generalizes well and isn't overfitted to a particular subset of the data. K-fold cross-validation. The data is divided into K subsets, or folds. The model is trained K times, each time using K1 folds for training and the remaining fold for testing. The performance is averaged across all folds to give a more robust estimate of model accuracy. Leave one out cross-validation, LOCV. In LOCV, each data point is used once as a test set while the rest are used for training. It's an extreme form of cross-validation where the number of folds is equal to the number of data points. 6. Hyperparameter. Tuning hyperparameters are parameters that are set before training a machine learning model and affect the model's learning process. Hyperparameter tuning involves finding the best set of hyperparameters for a model. Grid search. A technique where you manually specify a range of hyperparameters, and the model is trained with every possible combination. The hyperparameter combination that results in the best performance is chosen. Random search. Unlike grid search, random search selects random combinations of hyperparameters, which can be more efficient when the search space is large. Real-world application. Predicting customer churn. A telecom company wants to predict whether a customer will churn, leave the service, based on various customer features such as usage, contract length, payment method, and customer service interactions. The company uses a supervised learning algorithm like logistic regression or random forest to make predictions. 1. Data collection. The company collects data on customer demographics, usage patterns, and historical churn data. 2. Feature engineering. The data is pre-processed to handle missing values, normalize features, and create new features, e.g., customer tenure in months. 3. Model training. The logistic regression model is trained on a labeled dataset, where the label is whether the customer has churned 1 or not 0. For model evaluation, the model's performance is evaluated using metrics such as accuracy, precision, recall, and the F1 score. 5. Deployment. The model is deployed to predict whether a new customer will churn, allowing the company to target at-risk customers with retention strategies. Glad you could make it to the end of the module. Take the quiz to continue to the next module.